7.2. It's a cantilever beam and it has a uniformly distributed load and it has a moment at the end. So there are multiple ways to solve this beam. So basically what we are trying to do is that we are trying to calculate the elastic curve, which is the displacement or the deformation of this beam. So there are multiple ways to do this. One is the most nice way is to use equation method, where you have to calculate the reactions first, and then you have to cut a section, call it x, the distance where you're cutting a section, and then you can determine the equations for shear force, bending moment, bending angle, and also the elastic curve, which is the displacement curve. And you can get those equations, and using those equations you can just draw shear force and bending moment diagrams and the bending angle diagram and also the displacement or the elastic curve. The second method is graphical method, which we have explored last time. And the third method is superposition method, which we will do today. And in this method, basically what we have to do is that we have to make use of the equations which we already have for a particular loading conditions. So we're gonna use these equations, and from those equations we will just formulate our elastic curve. So this table, it gives you the equations for a known loading conditions and the known beam types, and it gives you the maximum slope values, it will give you maximum deflections, and it will give you an equation for the elastic curve as well. So for those who don't have the appendix, I have printed out, so you can take it, but I guess most of you guys have. I think you don't have, right? So you can take one page from here, but yeah. So we're going to use these equations. So the last column is the elastic curve column, is the displacement column. So we're going to use this. So this is our problem, right? So last time we used the equation method, and this is what we got. We got 4 equations, and we can use those 4 equations to draw all the diagrams we need. And this one is graphical method, which we did last time. And the graphical method is basically you have to integrate the loads to get the shear force, and you have to integrate the shear force. Integration means you just have to calculate the area under the curve till you need to calculate the value. For example, if you want to calculate the value at this point for the moment, you will go to the shear force and you will calculate all the area of the shear force, and that will give you a moment value at that particular point. So wherever you want to calculate the moment, you just calculate the area of the previous all the distances, and then you will get the value of the moment. Similarly, you can get the values for the bending angle and the displacements, but you also have to divide by EI for the bending angle, because that's the equation to calculate the bending angle from the moment. But the idea is you integrate the loads, you will get shear force. You integrate the shear force, you will get bending moment, and you integrate the bending moment, you will get the bending angle divided by EI. And if you integrate the bending angle, you're gonna get the displacement curve. But for the bending angle, you also have to be aware of the boundary condition. So it's a fixed support, so we know the bending angle is 0, and we also know the displacement is 0 as well. And we'll go from there. So that's the graphical method, which is a little confusing at times because, I mean, in graphical method, it's easy to make mistakes. So it's always nice to use the equation method. And now we're going to use the final method, which is called superposition method. So this is our beam. It's a cantilever beam. It has 2 loads. One is a uniformly distributed load of 10 kilonewton per meter, and we also have a moment. It is an anti-clockwise moment with 30 kilonewton meter. So now we will draw the elastic curve, or we'll figure out the displacements for the entire beam using superposition method. So this is a cantilever beam, and it has two loadings. It has a uniformly distributed load of 10 kilonewton per meter, and it also has an anti-clockwise moment of 30 kilonewton meter. So we can go to our appendix, and we can see in this appendix that the first page is about simply supported beams, right? All the loading conditions are for the simply supported beams. But in our case, we have a cantilever beam. So we'll go to the next page, and we'll try to see which figure is more related to our case. So we have uniformly distributed load and we have a moment. So what do you think, which equations are more relevant in our case? So I would say that this is a cantilever beam with a uniformly distributed load, and we also have a uniformly distributed load. So this is the case which is relevant to us, and we also have a moment, right? We also have an anti-clockwise moment, and we also have a cantilever beam. So these two beams are more related to us, and so we'll use these values. So if we want to calculate the maximum bending angle, we can just use these equations. If we want to calculate the maximum displacement, we can use this equation. But we want to we want to calculate the elastic curve for the entire thing. So we'll use these two equations, right? So basically, our case is a combination of these two values, right? So we're gonna calculate this separately, we're gonna calculate this separately, and then we can add them together, and that's gonna give us the result for our case. So this is a uniformly distributed load equation, right? This is for uniformly distributed load. So I'm gonna put it here, and this equation is for the moment, right? So I'm gonna put this equation here. So basically we need these two equations. This equation is for the case where you have a uniformly distributed load. And this equation is for the case where you have only moment. So I'm going to divide this into 4 parts. This is x is equal to 0, this is 1, this is 2, this is 3, this is 4. Similarly, this x is equal to 0, this is 1, this is 2, this is 3, this is 4. So we can use this equation and we can just draw the elastic curve. So in this case, m naught is 30 kilonewton meter, and EI is, we already know this, which is 20,000 kilonewton meter square. So you can use this and you can draw so if I use x is equal to 0, then we would be m naught, this is going to be 0, so we're going to get 0 value. That's our 0 value. So if we put x is equal to 1, then our moment is 30 kilonewton, so Newton meter, multiply by x is 1, so this is going to be meter square, 2 into EI, E is 20,000 kilonewton, so 10 raised to the power 3 Newton meter square. So this is going to cancel out, this Newton is going to cancel out, this meter square is going to cancel out, so you only have a meter left. So we would be equal to it would be equal to 0.75 millimeter. So I also have multiplied by, I multiplied by 1000 because it was in meter. So this value I'm getting in meter, so I just multiplied by 1000 and I got 0.75 millimeter. Similarly, if you put x is equal to 2, you're gonna get 3. If you put x is equal to 3, you're going to get 6.75. And if you put x is equal to 4, you're going to get 12. These are all millimeter. So now we can just plot this. This x is equal to 0, v is equal to 0. I plotted this. X is equal to 1, v is 0.75. x2 is v3. x3 is 6.75. And x4 is 12. So that's how you can draw the displacements for this case. Now you can also draw the displacement for this case, and then basically you have to add them up, and if you add them up, you will get the total displacements, which should be similar to what we have got from the graphical method and also from the equation method. So everyone, you can try to draw the elastic curve for the first case using this equation. And in this equation, our W is 10 kilonewton per meter, and EI, you already know, is 20,000 kilonewton meter square, and length we know is 4 meter. So you guys can calculate, and once you have the answers, so we can just add these two things and we're going to get the final value, right? So at x is equal to 0 for the, so let's say this is first part and this is second part. So I'm gonna, this is first part, this is second part. So the first part, for x is equal to 0, the displacements were 0. For x is equal to 1, I got here negative 1.69. This is in millimeter. So everything is in millimeter. This is everything is in millimeter. And here I got 0.75. When x is equal to 2, I got negative 5.67. and here I got 3. For x is equal to 3, I got negative 10.69, and here I got 6.75. When x was 4, I got negative 16, and here I got 12. So all I have to do is that I have to add these values. So 0, 0 is 0 millimeter, minus 1.69 plus 0.75 is negative 0.94 millimeter, minus 5.67 plus 3 is negative 2.67 millimeter, negative 10.69 plus 6.75, I'm gonna get negative 3.94 millimeter, and here I'm gonna get negative 4 millimeter. So our final answer is, this is for the displacement curve. So I have 0 value here, and then 0.94 negative here, and then negative 2.67 here, and negative 3.94 here, and 4 here, negative 4. So this is what I will get. And it's the same as we got from the graphical method, and it's the same as we got from the equation method.